In December 2021, a telescope the size of a tennis court launched into space, folded up like origami inside a rocket. It traveled 1,000,000 miles from Earth, unfolded itself in the cold vacuum, and pointed its golden mirrors at the oldest light in the universe. Within months, astronomers noticed something odd in the background of Webb's first deep images. Tucked between the swirls of ancient galaxies, scattered across multiple observations, hundreds of tiny bright objects kept showing up. Red, compact, impossibly luminous. And according to every model built over the past 30 years, they should not have been there. For 3 years, these objects have been quietly dismantling what we thought we knew about how the universe began. And we may finally know what they are. Light takes time to travel. When you look at a galaxy 10 billion light years away, you are seeing it as it was 10 billion years ago. Webb was designed to see further back than any telescope before it, all the way to the first few 100 million years after the Big Bang. Back then, the universe was barely out of its infancy. The first stars had only just begun to flicker on. Galaxies were supposed to be small, faint, messy clumps of gas still figuring out how to pull themselves together. Webb found the opposite. It found galaxies that looked mature, organized, massive. Some rivaled the Milky Way in size, and the Milky Way took 13 billion years to get that big. These galaxies seem to have done it in under 1 billion. To grow that fast, they would have needed to convert nearly all of their available gas into stars. Normally, galaxies convert about 10%. These would need close to 100. Nobody had a good explanation for that. But the truly strange objects were something else entirely. Smaller, weirder, and much harder to explain. By the summer of 2023, several research teams had published papers on a specific category of objects in Webb's data that did not fit any existing classification. They were tiny. Some were just a few hundred light years across, about 1,000 times smaller than the Milky Way. Their light was wrong. When astronomers split it into a spectrum, they saw a distinctive V shape, bright at both ends, dipped in the middle. That pattern did not match any known type of galaxy or star cluster, and the hydrogen gas inside them was moving at thousands of kilometers per second. Whatever these objects were, something inside them was extremely violent. A researcher named Matthee gave them a nickname in 2024, Little Red Dots. Simpler than the technical term, broad-line H-alpha emitters. It stuck. As of 2025, Webb's data contains 341 of them. All existed within the first billion years of the universe. Most of them cluster around the 600 million year mark. The universe at that point was barely 6% of its current age. So what were they? The first idea was that they were ultra-dense pockets of stars. Enough stars packed into a tiny volume could explain the brightness, but the spectral signature was wrong, and the density required would break every record by a wide margin. Stars alone could not produce what Webb was seeing. The second idea was that they were supermassive black holes at the centers of tiny galaxies, actively consuming matter and outshining everything around them. That fit the spectral data better. But the scale was off. The black holes would need to be absurdly large compared to the galaxies hosting them. In the modern universe, a central black hole is typically 1/10 of 1% of its galaxy's mass. In these objects, the ratio would be 100 times higher. Neither idea really held up. In late 2025, a third explanation started gaining traction. A weirder one. It goes like this. What if the universe had a shortcut? In the standard account of black hole formation, you start with a massive star. It burns through its fuel over millions of years, collapses under its own gravity, and the core crushes down into a black hole, typically a few times the mass of the Sun. Over billions of years, these stellar black holes merge and grow into the supermassive monsters at the centers of galaxies. But that process is slow. Way too slow to explain a supermassive black hole existing when the universe was only 600 million years old. The math does not work. There has not been enough time. Direct collapse black holes skip all of that. In the very early universe, there were regions where enormous clouds of pristine hydrogen gas had never been contaminated by heavy elements. Heavy elements are what allow gas to cool, to fragment, to break into smaller clumps that become individual stars. Without them, the gas stays hot. It cannot fragment. And if the cloud is massive enough, the whole thing collapses at once, directly, into a single black hole. No star phase, no gradual growth, just a sudden collapse of an entire gas cloud into a black hole potentially tens of thousands of times the mass of the Sun. Theorists had predicted these for over a decade. Nobody had found one. They were supposed to be the heavy seeds, the starting points that could explain how supermassive black holes got so big so fast. The little red dots might be exactly where they have been hiding. In January 2026, a team published a paper with radiation hydrodynamic simulations, computer models that track both how gas falls onto a black hole and how the radiation from that process affects everything around it. The results lined up with what Webb was seeing. A newly formed direct collapse black hole, actively consuming gas, would be surrounded by a thick cocoon of ionized material. The black hole's gravity pulls gas inward. Friction heats it to extreme temperatures. It radiates enormous amounts of energy, but the radiation does not escape cleanly. It gets trapped and scattered inside the dense cocoon. That scattering produces the broad spectral lines Webb detected. Not because the gas is moving at extreme velocities, but because the photons are bouncing around inside the cocoon, getting smeared out. And the radiation filtering through the cocoon is what gives them their red color. They are young black holes, 100 times less massive than astronomers first estimated. Wrapped in a glowing shell of gas they are actively devouring. The simulations match the brightness. They match the spectral signature. They match the size. And they explain something else, why these objects appear and then vanish. The cocoon phase does not last. Once the black hole consumes its surrounding gas, it transitions into something more familiar, a normal active galactic nucleus at the center of a growing galaxy. The little red dots are not a glitch. They might be the missing link, the moment a primordial gas cloud becomes a supermassive black hole. Every large galaxy in the modern universe has a supermassive black hole at its center. The Milky Way has one. Andromeda has one. Every galaxy we have looked at closely enough, same thing. But for decades, nobody could explain how those black holes got so massive so early. The universe should not have had enough time. If the little red dots really are direct collapse black holes caught in the act, that is the answer. The heavy seeds existed. The shortcut was real. The universe did not need billions of years of patient merging. It had a faster way. Webb found 341 of them in its first few years of operation. Nobody knows how many more are sitting in data that has not been analyzed yet. 3 years ago, these were background noise. Tiny red smudges that astronomers almost scrolled past. Now they might hold the answer to one of the oldest questions in cosmology. How did the first massive structures in the universe form so fast? Webb was built to see the oldest light in the universe. Turns out, the oldest light had a few things hiding in it that nobody expected to find.